land in the country is used for cotton. There's 6 million cotton farmers, huge numbers. 40 to 50 million people in all engaged in ancillary activities around cotton. The problem with cotton is that it's particularly vulnerable to pests. And this is a cause of low yield. For example, in India, the average yield per hectare is 480 kilograms or so, whereas the annual average, the worldwide average is closer to 750. 30% of yield is estimated to be destroyed in pest attacks. And of these pest attacks, 70% is caused by what are known as cotton bollworms that attack the cotton boll. As a result, nearly half of India's pesticide usage is on cotton, right? And this is bad for the environment. This is bad in all sorts of ways. It's costly for the farmer. It's bad for the environment using pesticides. And they're so scared of pests that they indiscriminately, spray pesticide, right? And this is the problem we wanted to see if it could be addressed using AI. Various consequences of overuse of pesticides. What we built was an app called CottonAce, which is an AI-based early pest warning and instant advisory system. It's fairly simple in use, but it solves an important problem. So the problem that it's solving is it helps farmers protect their crops before they are attacked by pests, or before they are significantly attacked by pests. It also helps the agricultural program officers manage these programs well, and it replaces a manual system that has been going on for decades. And the manual system works as follows. So typically there's a lead farmer in a village who installs a pest trap. The pest trap is not really meant to destroy the pests. It's more meant to get an estimate of how many pests there are, right? So the pest trap catches a few pests. They take a picture of the pest trap, and then when they're connected to the internet, they send it to the local agricultural university. The agricultural university looks at the pests on the trap and gives them feedback on whether they should spray pesticide or not. And this entire manual cycle takes a week to 10 days. By the time often the farm is already attacked by pests and it's too late, right? So we wanted to replace this with a computer vision-based advisory. And I should mention this project won the Google.org Impact Challenge Award a few years ago. It also won the H&M Global Change Award, I think 3 years ago. The app is multilingual, works in 9 languages. It's very easy for the farmer to use. It allows inference on edge, offline. It doesn't need internet, and it gives you real-time alerts. So this is sort of what the cotton plant looks like after the bollworm has infested it. And the way, sorry, you can't see video on this, but that's okay. The way farmers use the app is they first install a trap. So there's a demo farm in a village. A demo farm is sort of a representative farm, and it's defined by a farm in which the farmer can afford to have a smartphone and can afford to buy a trap, right? So they install a trap on the farm. Every couple of days or so, they are supposed to empty the contents of the trap onto a piece of white paper. And the image looks like what you see there, the second picture there. This is actually a very clean image. A typical image looks like, there's a bunch of these bollworms, these pests. There's dirt. There's all kinds of other pests. It's all mixed up. And so the farmer takes a picture of that image through the app, and then the app gives an advisory on whether they should spray or not, right? So it's fairly simple. What the model is doing in the back end is it's just counting the number of pests of a certain type, right? So it needs to learn to recognize the pests, and it needs to count them. So at the back end, it's an explainable model in the sense that there are bounding boxes around every pest. So if the model is doing something wrong, it's possible to figure out what's going wrong. And then once this advisory is sent to the lead farmer, then there is, the lead farmer is connected to all the other farmers in the village, and the advisory is then transmitted to all the other farmers, and that's how we achieve scale. So the data for this, it's about 16,000 images that we collected in the field. So the 16,000 images includes data collected from the field and then human annotated with bounding boxes. Data that we received after we did an initial pilot deployment. So we had that data that was again annotated. And then we need sort of negative data, images without pests. And we use the Akogo data set, which is a large sort of image segmentation data set that's open source. And what the app does currently is identify the two major pests that attack cotton farms. That's the American bollworm and the pink bollworm. There's huge data challenges. Even though the modeling looks sort of simple, there's huge data challenges in this. There's occlusions, there are tiny pests, camera resolution is low, out of focus images. There's lack of diversity in the data, not enough counterexamples. So for example, if the farmer took a picture of a white wall with smudges on it, that can throw off the model, things like that, right? Majority of the pests are small and dark, and that looks very similar to dirt, right? And then, there's other sort of data split issues that, we've solved, and then bad annotations as well. So you need expert annotations on data like this. If you take an image like this to a typical entomologist, they're used to seeing images of live pests. They're not used to seeing images of dead pests. So they often make mistakes. Sometimes, single pest is scattered all over the image. So there's huge issues like this. So we had to go through a lot of data quality iterations, modeling iterations to get this right. So these are some examples. On the left, you see an occluded image where you have a whole bunch of pests sort of occluded together. It's impossible even for a good computer vision model to be able to count the number of pests on this. Tiny pests and so on. So I'm not going to go through all of these. And this is what the modeling workflow looks like. So you should really read this from bottom to top. You have input image that goes into the phone. And there's first a rejection model that tells you whether this is a valid image of a trap or not, or whether it's something else. And if the rejection model rejects it, the farmer is encouraged to retake the image. If it's accepted, then there's an identification and counting model that counts the number of pests. And then depending on the output, we also have conformal prediction on top of this. So depending on the output, either the output is accepted, or if the uncertainty is too high, the model abstains from taking a decision. If it abstains, it goes to a better model that sits on the cloud. So the image is then transferred to the cloud. And this cannot happen in real time. It can only happen when the phone is connected to the internet. So it syncs up with the cloud. And then we have a larger model on the cloud that does the same thing. If the larger model abstains, then you have a human-in-the-loop workflow. So that's how we ensure that this whole system is high accuracy. Yeah, so the phone model is based on the YOLO V8 architecture, which is a very popular segmentation architecture, which we retrained from scratch on this data. Actually, no, we didn't quite retrain from scratch. We used the starting weights from training on Akogo and then started off from there. So a bit of transfer learning. On the cloud, we have a much larger version of this model, the YOLO V5. And so that's how the workflow goes. And then we have a rejection model that's also a version of YOLO. So some results, the columns that you see, the MAE is the mean absolute error, PBW is the pink bollworm, ABW is the American bollworm. So the mean absolute error looks kind of high. This is the error in the count. So 3.66 would be an error in the count of the number of pests. It turns out that this error is dominated by the clumping phenomenon that I showed you earlier, where you have pests clumped together. And so if you throw away predictions larger than 20 in computing the error, and that makes sense because if there's more than 20 pests on your trap, you're supposed to spray pesticide anyway. It doesn't matter what the AI is telling you. So if the AI estimates more than 20, if you remove that from the error calculation, then you get this MAE at 20, which is really well controlled. It's less than one count per image. And you can see the phone model is small enough to fit on a basic smartphone, 45 megabytes. The rejection model is extremely accurate. And this is the effect of abstention. The accuracies before, this is the accuracy on false alarms. The accuracy before extension is around 91%. After, if you include abstention in the workflow, the accuracies go up to 95, 96%. So we've deployed this over the last 3 or 4 years in various settings, and then we've measured the effect of farmers using this, right? And I'll just quickly go through the results. I'm aware of time. I want to get to another project as well. We get, farmers who use this app report 17% better yield, 8% better price due to better quality of cotton, and so on, 26% reduction in pesticide cost, 20% increase in profit. And what we've done right now is currently this is integrated into a much larger national pest surveillance system in India that includes both sort of trap-based images as well as images of plants, direct images of plants that are infested. And we built models for those as well. So it's currently being used. The next project I know I have 5 minutes left. I'll spend the next 5 minutes talking about another project that's in progress. This is a healthcare project where we're trying to screen for TB using solicited cough sounds. Right? Again, TB is tuberculosis is a huge problem in India. It has the world's highest TB burden, I think, just because of population numbers. 25% of the world's TB cases are in India, and about 30% of the world's TB deaths. And in spite of these numbers, it's estimated that about 64% of TB cases are just missed by the system because people don't get screened. People, there's huge sort of social taboos around TB. So if they're coughing or if they show symptoms, they don't go and see a doctor. Diagnostic tests, these are typically molecular tests that detect the bacterial DNA within sputum. These are very expensive and therefore not scalable in rural areas in India and Africa. Chest X-ray is a standard screening method for TB, but that's also not very scalable in rural areas. You need large equipment in jungles, in remote areas, and so on. And so screening is typically done through self-reported symptoms. There's the classic sort of 7-symptom rule that people use. If you have these 7 symptoms, then you should go for confirmatory sort of genetic testing for TB. So our long-term aim with this project is to develop a high-sensitivity TB screening rule that can be used in remote areas, that can be used in the field. And so it has to be cheap, it has to be compact, scalable, and this was really inspired by our work on COVID, where COVID has a very distinctive cough signature, as you all probably know. TB does not. So this is a much more challenging problem than the COVID problem. And this is based on solicited cough and self-reported symptoms. So we have some encouraging results. I won't go through all the details. So we take 3 cough recordings per patient, and then the patient sort of reports whether they have one of these 7 symptoms: cough, blood and cough, fever, chest pain, etc. And also if they have any known comorbidities like diabetes or COVID, or if they're alcoholics and so on. And then the model in the back end gives a prediction of whether you ought to go for confirmatory testing. The data collection problem was huge here. It's very difficult to convince random people to go for a TB test, given the sensitivities around having TB. And TB is a very low prevalence disease. I think it's 0.04% or something like that. So you have this sparsity problem. As a first pass, what we did was there are TB health clinics throughout the country. And we went to TB health clinics and collected random samples from patients. And for negative samples, we asked the workers in the health clinics to contribute their cough sounds, right? So that was sort of negative data. And then later, in addition to this data, we also collected data from contacts of TB cases, immediate family members and so on. And then we collected data from individuals going in for a chest X-ray at public health facilities for any reason, right? So we have a mix of these various data sets, and they have very different prevalences of positives and negatives. So it's a very challenging machine learning problem. There's data mixed across different domains, different prevalences of positivity. The facility data had the highest TB prevalence because these are TB facilities. You expect most of the patients to have TB. So roughly half the patients there had TB. On the other hand, the health workers are expected to be mostly negative. So very few had TB. Contacts of TB cases, we got 3% prevalence of TB. And X-ray facilities, because it was general X-ray, again, very low prevalence. Not going to go through a lot of modeling details. Essentially, again, we built a cough detector model that detects whether something is really a cough sound or not, and that's a very high accuracy model. And then the model analyzes the cough sounds and the tabular data, the symptoms, and we create an ensemble model that gives an output. And yeah, so the cough detector is very high accuracy with an AUC of 0.99. And then we do pre-processing on the cough. We take the audio recording, convert that to time, frequency, space, do a MEL transformation, so you get what's called a MEL spectrogram. We did data augmentation by masking time and frequency regions, very small time and frequency regions in order to create a larger data set. And a lot of things that had to be done to the data in order to get the model to work reasonably. So I'll just skip straight to the results. We do aggregation across cough sounds. This is the tabular data that we collect. And relative to symptomatic screening, the results are not great. So there's three types of models: a cough-only model, a model based on symptoms alone, and a combined ensemble model. And we look at specificity at a sensitivity of 90% and sensitivity at a specificity of 70%. And you can see the cough-only model doesn't do great. And this was discouraging in the beginning, but then what we found is that, sorry, I have to skip a few slides. What we found is that if you restrict the analysis to those who don't have symptoms and are TB positive, the cough-based model does a lot better than the other models. So cough seems to capture some signal for TB that's not present in symptoms. So it's very good at detecting asymptomatic or pre-symptomatic TB cases before they get symptoms. Right? And then we've deployed this in various settings. And what we found is that consistently, if you look at our deployments across time, we consistently find between 12 and 14% additional yield of TB cases due to the cough sound alone. And these are all asymptomatic TB patients. So we think there's a lot of promise in this. We continue to develop it. What we need is further data from community settings and basically asymptomatic TB positive individuals. That's our biggest challenge, getting people who don't have symptoms to volunteer for a TB test. And then, of course, we need to build interpretability around all of this. We want to be able to isolate parts of the cough that carry the TB signal and also be able to map the AI score to the severity of TB. But this is where we are right now. Thank you. Happy to take questions. These are the two teams. Lots of people worked on these projects, especially because of deployment issues.
We have set it up Slido, so people joining us online can post their questions on there. So anyone has a question?
Thank you very much for the talk. I was wondering, I'd love to hear your perspective on what you think needs to be improved or changed to make rolling out these models or these sort of applications easier. Is it on the hardware or software side, or is it mainly social, perhaps?
It's mainly data, that much better data gathering systems at scale. It's the problem in these situations is really at the two ends of the AI. getting better quality data, and having deployment platforms so that you can create impact at scale. The modeling is the interesting problem, but it's easier than these two.
Thank you.
Just following on from that, you said you had problems with your data annotators. How do you get over that? I mean, bad quality data, I presume it's disagreement between annotators? Or?
Yes, so we had to account for annotator disagreements, and we had to hire entomologists to annotate the data, and then we took sort of consensus majority votes on annotators. But there are other ways to do it.
Out of curiosity, what was your inter-annotator agreement?
On the counts, I think on the false alarm, so there's thresholds on the counts. If the count exceeds a certain number, you have you have a recommendation to spray pesticide, and that number varies season by season, and that's computed by entomologists. It's called the economic threshold limit. So if you, I think, I'm trying to remember. So on the final recommendation, not on the count, on the final recommendation, the inter-annotator agreements were fairly high, in the 80 to 90% range. But on the actual counts themselves, they were pretty low, maybe 50, 60%. So, yeah.
Thank you very much for the great talk, Alpan. I was wondering, you mentioned a lot about the data source of the TB being very imbalanced between the negative and the positive cases, which I assume cause bias in your model. I wonder how you're actually going to encourage people to come forward who potentially are asymptomatic TB sufferers, what the strategy is that you're going to put in place for that.
Yeah, so from a modeling perspective, so far what we've been doing is only training on the facility data, which is 50% positive, and then using the other data sets for evaluation, for hyperparameter tuning and evaluation. Going forward, I think getting normal individuals to do TB testing, we have to piggyback on what are called case finding efforts. So there's prevalence studies that go out in the community and try to figure out what's the prevalence of TB in the community by region. And what they do is they use statistical methods to sample individuals at random and then test them for TB. And what we're trying to do is collaborate with the agencies that do this so that we also capture cough sounds when they're doing this. But this happens once every 4 years or so. So I think we have to wait a year before we can get that data.
Thank you.
Hi, thank you. I was wondering, one of the boons from the pest control was reduced pesticide use. Are there any measures of biodiversity being maintained or increased through the use of this? And is there any opportunity to gather that as a kind of residue from your images, or are the traps too specific?
That's interesting. We've never thought of that. You mentioned biodiversity, right? No, we haven't thought of that. So, and I don't know if that information exists in the images.
Are the traps too specific? But you mentioned a pheromone.
Yes. So we have trap-specific images, but I don't know if that's going to tell you much about biodiversity.
I'll squeeze in a second one. I was curious how many people, and you mentioned, and you put up a list of people, which looked like 30 to 40 people or something like that. I was curious what kind of timescale it took you to put together these things and get to a result.
Yeah, so for the cotton project, we've been working on it over the last 4 years. The TB project, about 2 years. These are fairly long timescale projects, mainly because of the data collection and so on.
Yeah, it's fine. We can just take one last question for now, if that's okay.
I noticed on the company GitHub that you've run a couple of competitions to try and make new models. Have you had much success with opening it up to the community and running those sort of challenges?
Yes, so for the cotton model, we got the YOLO idea from a competition. We were using a single-shot detector model earlier, and the YOLO models work a little bit better.
Great, thank you.
Thank you so much. Yes, it's okay. Like we can set up. So next up, we have Professor Maria Liakata. She is a professor in natural language processing in Queen Mary University of London. I'm so sorry. She also co-leads the NLP and data science for mental health interest groups at Alan Turing Institute. Her work has contributed to advances in knowledge discovery from corpora, automation of scientific experimentation, and automatic extraction of information from the scientific literature. And she's going to talk about today AdSolve, addressing socio-technical limitations of LLMs for medical and social computing. So let's go.
Thank you very much. Can everyone hear me well? Great. So yeah, we're very excited. I'm very excited to be here, and we're very excited about this new project it's a Keystone project funded by RAI UK and UKRI on addressing socio-technical limitations of large language models, particularly for medical and social computing. So as I'm sure many of you know, large language models are state-of-the-art algorithms trained on large amounts of textual and multimodal data, and the popular technology, the technology behind very popular systems such as ChatGPT, but also multimodal foundation models. And they have impressive performance in generating human-like text, as well as creative content, multimodal content, translating across languages, answering questions in an informative way. However, they have known technical limitations such as biases, privacy leaks, poor reasoning, lack of explainability, and all of these raise concerns about their use in critical domains such as healthcare and sort of science as well more broadly. So what are we trying to do in this project? So we want to essentially create an extensive evaluation benchmark which includes novel criteria and metrics and tasks for assessing the limitations of large language models in real-world settings, particularly in a medical context, and take a responsible and ethical approach. We also sort of considering and knowing these kind of limitations, we also are working on devising novel mitigating solutions based on new machine learning methodology, but also informed by expertise in healthcare, ethics, and law. So there's sort of, I'll talk a little bit about the use cases, and via co-creation with domain experts. And the kind of methodologies we're working on are development of modules for temporal reasoning. We know these models are really bad at sort of doing longitudinal tasks and sort of understanding the order between different kinds of events. Situational awareness, particularly in long-form text. Dialogue and multimodal data. So alignment with human preferences, particularly in a cross-modal setting, bias reduction, and privacy preservation. So a little bit about the team. So this is quite a large project. There's 12 co-Is, I'm PI, and from 4 different institutions, Warwick, Sheffield, Queen Mary, which is the lead, and Nottingham. And we have a range of expertise among ourselves. So we have NLP experts, vision experts, people who've been working on responsible research and innovation, social computing, ethics experts, but also experts in psychiatry and law who are kind of the domain experts for the use cases. And we have a range of different multidisciplinary teams and partners involved here, and our partners range from large conglomerates such as Microsoft, Accenture, Bloomberg, Canon Medical, to more specialized companies in healthcare. We have legal companies and NHS trusts, NHS England, research centers, and also standards and regulatory bodies. So importantly, what we're trying to do here as well is make sure that in each part of the project we have people involved from different levels of expertise, so that there aren't kind of siloed work packages with people, for example, in computer science working on a specific let's say, mitigation methodology without the sort of domain experts being involved. So the project itself, the way it's structured, and I'll go more deeply into kind of current progress, involves 3 main use cases. So we have a use case in multimodal medical diagnostics, where we're particularly interested in multimodal longitudinal monitoring, as well as bringing together sort of the different modalities for diagnosis. We have a use case in AI support for mental health, where, as well as the longitudinal monitoring, what we're looking at is as well as better ways of doing summarization, especially with a better understanding of temporal ordering of events, and also dialogue-based self-management, which at the moment this is not really feasible. And then finally, we have a use case in legal support, which again covers particularly summarization of documents, legal documents, court cases, and dialogue system for legal advice. And then we have these work streams that are cut across these use cases, where we have things like a sort of an overarching work stream where we look at requirements around what experts need in terms of working on the ground with these kinds of systems, and this involves co-creation workshops and a lot of sort of engagement with stakeholders. We have the second overarching work stream, which is around evaluation, which takes this kind of feedback, but also very much sort of is around the operationalization of requirements into large benchmarks and evaluation tasks. And I'll talk a little bit more about this in more detail. And then we have the strictly more technical work streams, which are around improving the temporal reasoning and the situational awareness, but also things like privacy preservation and then finally, sort of the kind of the multimodal aspect of diagnostics. And so there is, as I said, a lot of sort of engagement with stakeholders. So I guess the main thing to take out of this is that we're starting from December, which is kind of the launch of the I guess our launch event and the first main workshop with stakeholders. There's going to be these kind of interactive workshops every 3 months. And so if there are people who are interested, you can contact me, because we're still, even though we have a large set of partners, we're still looking at broadening our scope in terms of our stakeholders. So what are we actually doing in this project? So obviously this project started in May, but obviously it also builds up on work that we've already been doing in this direction. So we have been working on new methods for evaluation, particularly based on atomic natural language inference, and hopefully there'll be more time to talk about this, cross-model alignment with preference data, synthetic data evaluation, and we have a paper that I'm going to talk about on synthetic data, on a synthetic data evaluation benchmark. We're working on synthetic data for privacy preservation, particularly in the NHS, temporally aware summarization in mental health, and I'll talk more about this, modules for temporal reasoning, and looking more broadly at reasoning limitations of LLMs. So we're currently preparing this large survey paper. And then the next steps will be around working with multimodal data sets, and particularly we're going to be working with pancreatic cancer, explainability of large language models, and personalized generation and monitoring for dialogue. So I'll talk a little bit now more, zoom in into some of the work that we've been doing. So in terms of an evaluation framework. We've just had this paper accepted in the Journal of Computational Linguistics on sort of this framework for evaluating synthetic language data. And now, why do we actually care about this? Why is evaluating the quality of language data, of synthetic language data, important? Well, for one, a lot of the current use of large language models such as ChatGPT and a lot of LLMs that people are using will be resulting in a lot of sort of artificially generated data out there. And so actually being able to understand the quality of this data is really important. And particularly, we have had a focus on synthetic language data from individuals, so from social media data. Now, another main interest in this is that the sort of social media platforms increasingly are not wanting to share their data. There isn't enough of good quality annotated data, and often also data cannot be shared. So having a good way of synthetically creating language data about individuals is important. And so what we do in this paper is we generate synthetic data using different strategies. So we use LLMs, but also we use techniques such as diverse paraphrasing, back translation, syntactically guided paraphrasing, differential paraphrasing, and we evaluate this in different ways. So one is through introducing metrics for intrinsic evaluation. Some of them are existing metrics, and then we also introduce some metrics based on natural language inference, and then we also evaluate them in an extrinsic way. So basically, there's this whole part which is around the intrinsic criteria, which are particularly looking at meaning preservation, style preservation, and divergence as a proxy for privacy. So you don't want basically your synthetic data to be exactly the same as your original, so you want it to be nicely paraphrased. And then we look at it from an extrinsic point of view, where you basically look at we basically look at tasks that show how useful this data is, and also how privacy preserving. So kind of talking a little bit more about the extrinsic evaluation, we basically have one task which is around looking at privacy preservation, and here it's sort of the idea is to check whether we can, if we substitute the data, if we substitute original data with synthetic data and train classifiers, how much are we likely to re-identify the original people, who sort of the people who had created the original data. And then in our and the second task is around looking at the usefulness of the synthetic data in terms of improving augmentation, for example, so you can use it instead of the original data, or use parts of the original data and parts of the synthetic data, and see how this affects the performance of downstream class tasks. And the other interesting thing about this is that we have considered tasks that operate at different levels of temporal granularity. And again, if you're interested in this, there's the paper, but also I can talk to you more about it in the break. So then I wanted to talk to you about our hybrid system for clinically meaningful timeline summarization. So this assumes that you have some kind of user-generated content like this, where sort of this is a timeline of posts from social media in this case, where an individual is expressing some kind of thoughts, and you can see that there is an escalation in their thinking, in their mood. So they're increasingly getting more and more upset, And so there's this kind of this sort of assumption that this timeline that you have at hand conveys this information, and we had worked on this in sort of previous publications, and now what we want to do in this work is this is also a paper from ACL this year, is to see if you can leverage this kind of information that is available in people's posts in social media for actually enhancing, augmenting, I guess, the knowledge that a clinician has about this person. Now, if you have the timeline as it is, it's actually very noisy. You can't really see what's going on with this individual. Yes, there's this kind of burst of emotions, but there's sort of events and things all over the place. So what we want to do here is actually take this noisy timeline and turn it into a clinically meaningful timeline summary, which can capture fluctuations in individuals' state of mind. And this can assist in sort of prevention and monitoring and early detection, and also organize information about a person's diagnosis in a way that is actually meaningful to a clinician. So basically based on aspects that the clinician finds useful. So we have been working closely with clinical psychologists, and they sort of offered a range of kind of different aspects that they were interested in, such as mental states, interpersonal and intrapersonal patterns, and sort of moments of change. And so what we wanted to do is essentially be able to translate this kind of the noisy timeline in something that actually addresses these aspects of sort of the mental state of the individual, their intrapersonal and interpersonal relations, and how basically and the sort of changes in their condition. So the way we've approached this was by having a hybrid system, which is based on a hierarchical variational autoencoder to structure an evidence summary. So it's essentially, this is like taking the timeline and creating a sort of compact first-person summary, and then translating that into a high-level summary that actually addresses the aspects that the clinicians are interested in. So what the diagram shows is essentially that you have this kind of way of creating this timeline summarization model that you then translate, and this is based on this kind of structural hierarchical VAE system, and then that timeline summary that results from there is translated via instruction prompts through an LLM into kind of this high-level clinical summary. And I guess I could say a little bit more about the system. So this is kind of the system for the first-person clinically meaningful timeline summarization, so for the evidence summarization part. And I guess the main thing here is how we get the structure, given that this is actually an unsupervised approach, so we didn't have enough summaries to train a system. So what we wanted is to use the VAE to essentially reconstruct parts of the timeline, which we call segments, and are anchored around kind of the points of change that I showed initially in the timeline, and basically this sort of the hierarchical VAE allows this kind of capturing relations between features and between segments. And then we have this the generation part, which sort of conditions these representations. So this is the part to the left, with sort of keywords that respond to kind of important aspects that are defined by clinicians, and sort of 3 or 4 annotated timelines. And again, if you're interested, there's the sort of the reference to this paper. and I have, I guess, very little time left for my the other work I wanted to talk about, which is around enhancing transformers so that basically they can become temporally aware. So so far there isn't a really good sense of temporality in these systems, and I guess what we've done is, for a range of different tasks where we actually are interested in capturing changes over time, and these can be at a different temporal granularity, so you could have these kind of moments of change in the social media timelines, which is the talk life one, but also you could have kind of more long-range changes, for example, in stance towards a rumor or topic shifts in a conversation. So we want to be able to have a system that captures change as well at different levels of temporal granularity. And essentially the solution we've adopted here is to actually modify the top layers of a transformer so that it can jointly model context and time dynamics. And there's the paper there, which is going to be presented at ENMNLP this year. And finally, yes, I just wanted to remind everyone about where we're going to. So we're still continuing with the work on temporality, which is very important in sort of a lot of the diagnostic tasks, not only in mental health, but also when you have things like X-rays from different kind of points in time. So any kind of longitudinal diagnostics, temporality is important. We're in the process of working with multimodal data sets for pancreatic cancer. We're already working on explainability of LLMs, but not published yet, and personalized generation and monitoring. So, and you can read more about sort of the current papers in this project. Sorry. Thank you.
Thank you so much. We are open for questions if anyone wants to go first. Perfect.
Thank you very much for the talk. Just looking at some of the example timelines there with this sort of very noisy data, I wondered if you ever have a challenge not almost doing a disservice to what the person is saying, and is it ever a challenge to ensure that the LLM is capturing some of the subtleties in the language? Do you have problems with things like irony, or if someone's downplaying what they're saying, or the opposite, where it looks like they're saying a lot, but perhaps they're, feeling fine?
Yeah, so this is why we're interested in sort of the synthetic language generation and sort of why, not just for privacy preservation purposes and augmentation purposes, but also for style preservation. And we're finding, for example, at the moment that things like disfluencies are not captured well. I think sarcasm, we haven't specifically tested for sarcasm, but yeah, it's sort of, I think it depends a lot on the context and how much it looks like other training data, whether that's being captured. But it definitely, things like disfluencies, which are important a lot when you're looking at mental health, for example, or a decline in cognition. So we're also doing a lot of work, I didn't mention this, but we're also doing a lot of work with dementia, and there, of course, capturing disfluencies is really important.
Perfect. Yeah.
So just following on from that, synthetic data, I mean, it's always, there are perils. I mean, how do you make sure you're not just learning artifacts from the synthetic generation mechanism and these sorts of things?
So at the moment, we're not training our LLMs on synthetic data and sort of releasing them. We have been focusing a lot on the evaluation of the synthetic data. according to different kinds of aspects. And so I think the kind of the meaning preservation aspect is where we're trying to make sure that this isn't happening. But it is an issue, and I think it's something that we can discuss later at the panel, what this means, this prevalence of synthetic data.
There's one question on Slido for you. It's what sort of collaboration are you open to if someone from the medical field with no AI LLM background would like to venture into? What would you advise?
So in terms of collaborating with the project, yes. So we want to understand how people work on the ground and how they envisage using these models. And we've had so far some conversations with regulatory stakeholders, and we found that the discussion was at a very high level. So what we want to do is sort of zoom in more into the use cases. And in our event in December, we plan to have a show and tell. So we kind of show, what are some things that we're thinking of doing, and then get feedback. So I think that's kind of really having this sort of concrete answers in terms of what the concerns are and what the practice is. And on what they would like to see. I think one of the challenges is that people don't necessarily, they know what they're doing now, but sometimes they can't imagine what they could be doing. And so I think the co-creation has this challenge in sort of trying to have this kind of iteration of show and tell and sort of feedback.
Perfect, thank you. We'll take one more question. Yeah, perfect.
Hi again, thank you for the talk. So you talked about reasoning and you've talked about temporality. One of the underlying issues that I think that a large part of the LLMs have is the coherence of an underlying world model. And I'm wondering whether you're struggling with that as well. So the idea there would be that if you don't have a coherent world model, that then relying on some type of temporal unfolding wouldn't be reasonable, it wouldn't be understood by the LLM.
So there has been work so far to try and address temporality in terms of at least temporal ordering of events. So there's different aspects to the temporality, right? One is understanding kind of the sequence of events in sort of reconstructing a timeline, and the other one is around being able to process the long form aspect of those, and sort of the temporal distance between events and what significance they might have, for example, in a diagnostic task. And so I guess in terms of having like this world model, there's been work that is trying to address even the notions of before and after, sort of getting that right. But a lot of the focus has been on pairs of events and not multi-event narratives. So this is what we're trying to focus on, is sort of bring in sort of this kind of multi-event narrative perspective, where we are sort of leveraging some annotated corpora on narratives for that. But there is also the issue around how we kind of better inject knowledge, real-world knowledge, common sense knowledge into these systems as a sort of components that can augment the reasoning. So there's different directions there for how you improve the temporal reasoning and reasoning overall.
Thank you.
Perfect. Thank you so much, Maria. That was really nice. Thank you. We are going to take a break for refreshments now before starting the next talk. And we'll be back here in 20 minutes. Thank you. Welcome back, everyone. So our next talk, our final speaker is here, Darlington Akogo. He has been named as one of the global 10 most influential people of African descent in healthcare. He is the founder and CEO of minoHealth AI Labs, an AI healthcare company, Kara Agro AI, an AI-powered plant and pest disease detection and precision agriculture platform, and Run Myla AI Institute, an AI and data science training institute. And his talk is going to focus on minoHealth AI, a foundation model for biology and healthcare. Please give a round of applause.
Thank you. So, hello everyone. I'm so happy to be here. Actually, there's a whole story behind it that we won't get into, but it took moving heaven and earth to make it happen. So super happy to be here. So we started minoHealth AI about 2 years ago. The goal was that, to give it a bit more context, minoHealth AI Labs started 2016, 2017, and we were focused on AI for health. So we built a number of models, right? So we're using deep learning and neural networks. But it was frustrating because you build a bunch of models and you realize there's always more use cases, there's always more diseases, there's always more dimensionality, more modalities in healthcare. So the dream was that would it be possible to ever build a single AI system that would potentially do everything in healthcare and everything in biology? That was the dream. 2 years ago, it seemed very possible. So leveraging the transformer architecture, we could develop a foundation model for healthcare and biology. So that's what led us to minoHealth AI. So minoHealth AI is essentially a multimodal large language model, right? Which is a whole lot of words stringed together. Essentially, a good way of looking at it is that it's kind of like ChatGPT, but then we built it ourselves. So it's a generative AI platform. But instead of making sure that it's able to, draft emails and stuff like that, we give it a whole lot of healthcare and biology data. So out of it, we got an AI model that we have different versions of it. So we have the one that is purely healthcare, and it has a number of tasks across healthcare. We'll get into that. But also we got a version that is an expert in biology. That's a lot of amazing things in biology. So we got an AI system that could do essentially biology, biochemistry, drug discovery. Within healthcare, it could do a number of things. So you're looking at diagnostics, prescriptions, treatment planning, triage, risk prediction. So we'll just go through a few of the things that we're able to get the AI system to do. We were able to get it to be able to describe molecules. So essentially, you could just give it. The advantage of this being a language model is that language or natural language, human language becomes the interface. So you could just ask it in plain English, French, Greek, whatever the language you choose is. It supports quite a number of languages. You could just give it some molecule and ask it to describe it for you to do that. It could give you the characteristics of it. And then beyond that, it could help you facilitate research. So this is an example, an actual screenshot of what this looks like. So you pass in the compound, you can ask it chemical features of this compound, and then the AI system will do exactly that. The next is looking at protein-protein interaction predictions. So it's able to map cellular pathways, identify therapeutic targets, and even optimize drug design. It's able to do all of this. So you can just pass in, for example, an amino acid sequence, and then ask it to 2 different amino acid sequences and ask it if there's any interaction. And in this use case, Okay, I think we'll probably get another slide. So it agrees that yes, there's actually an interaction between them. Oh, we don't have it here. But the next question is what gives confidence about your response to this particular case? Which is what makes this interface of language to biology or to healthcare super interesting. In the previous technology or technological attempts to anything within biology and healthcare, you get this one-off solution where you could possibly build an AI model that will predict protein-protein interaction, but it's a one-way thing. It predicts yes or no, so mostly a classification task. But the language interface allows you to then follow it up with a lot of questions, so it becomes more natural. It's a human, almost a human dialogue. So if you ask it to explain why it thinks there's an interaction, it could do that. You could have several conversations. It could go on for 20 questions back and forth, just discussing that one protein-protein interaction. The next thing has to do with molecule generation. So the AI system is able to do everything from textual descriptions. It's able to give you specified criteria, then help with drug discovery too as well. So, for example, in this use case, we passed in, so we give it a description and ask it what is the molecule for that, and it was able to come up with a molecule and then give you explanation of why that is the molecule. So it does exactly that. Then also the property prediction. So it's able to, even if it generates a novel compound and you ask it to come up with some in silico measurement for this, it could do this by itself. So you could check for things like the solubility, reactivity, toxicity, acidity. So for example, this is what are the chemical properties of this compound and its potential function. So it's going to pick up the compound, tell you the formula, the weight, the Small's representation, the appearance, solubility, purity, all of that in one go. So it can help you identify targets. It can help you understand the mechanisms of how this drug interacts with the targets. It can help you to optimize the designs for the drug in itself too as well. Then there's a cool use case. So, one of the things I actually find super, super fascinating about minoHealth AI and this approach that we took is that even we don't know the full limit of all that it can do. So what usually happens is that we are interacting with some biologist or some biolab, and then they present us with a use case and we go try it and we see that, oh damn, like actually can do that, which is super surprising. As a matter of fact, the idea of it being able to generate compounds is not something we directly trained it to do. We did not do that. We fed it a whole lot of like healthcare bio data, but we did not purposely train it to be able to help generate this. So to our surprise, it was able to do it, which was super shocking. But this proves a theory that if you sort of compile a whole lot of data and you feed it to an AI system, you get a system that actually exceeds your expectation. It's almost like, I'm not a physicist, but I'm kind of, at least, an enthusiast. So in physics, they are looking for the fundamental theory of everything, right? You want this one thing that sort of captures the whole physical laws of the universe. Essentially, the same thing happens with AI systems, which is that instead of building AI models and picking singular use cases, if you can bring in a whole pool of data, you find out that there's actually a pattern that connects everything together. And it's not always very clear when you look at it in the isolated use cases. So I'm sure, take for example, an oncologist or let's say a radiologist that is looking at mammograms in the hospitals might not necessarily see their work strongly connected to someone that is, designing antibodies for malaria. But essentially with AI models, nothing necessarily stops them from seeing some pattern that is over there. And one other thing that we realized from building this is coming to the conclusion that essentially all of knowledge, all of science, any field is just data analysis. It's just pattern recognition. You get some pool of data and you try to find a pattern in, and that pattern can be the discovery, or it could be an invention. Even that is still pattern recognition. New treatment, are you finding some pattern across some pool of data? And if that is the case, we human beings are phenomenal, but the reality is that there's a limit to how much dimension of data we could operate within. If you take human beings and you take computational tools, at least the old kind, that increases it to, let's say, a factor of about a few hundreds of dimensions. The good thing about foundational models, because you're looking at models that have billions of parameters, they are very, very good at operating across several folds of dimensions. And so the potential there is that they could see patterns that we could not. And so the mere fact that we saw a pool of data, because we know all the data we fed to the AI system, but none of it purposely was for designing drugs, but some way, somehow, across those patterns, I was able to pick up that as what they call an emergent capability, proves that there's a lot of patterns that we might not just be aware of. So that was a slight interesting thing that we found. So this was also another use case that we came across. The success rate of designing therapeutics is pretty low, right? Like it takes what? I think about 12 years and can cost up to $6 billion to make a single drug. And you usually will start with several tens of thousands of candidates, and then out of it probably end up with just a single one. That's terrible success rate. It implies that we do not have a firm grasp of the patterns across the data. So in this use case, for example, we thought, is it possible to ask an AI system if given a certain compound, or broadly let's just say therapeutic candidates, can it predict the likelihood that it will make it past the preclinical trial, and then explain why it thinks it can make it past that? And we actually were able to see it do that. So starting from this, we asked it to generate a possible smile representing a compound that could be useful for breast cancer therapy, and it did that. Then the next question was predict why. Oh, this is not the most updated, sorry. But yes, you can actually ask the AI system to explain it, go into a whole lot of details as to why it thinks it could make it past the preclinical trial. And the way to validate this is actually simple. So just take any approved drug that was approved beyond the pool of data that you actually use to train the AI system, and then see what are the chances of the AI system predicting that and the justifications that it offers. Yeah, so beyond preclinical trial, you could also do it for clinical trial too as well. So the good thing, again, with language as an interface is, since the focus of this is explainable AI, the AI system can actually explain its reasons, its decision making, which is different from at least the older versions, like your classification models and stuff like that. They usually would just say 0 or 1, or if it's multi-class, it's choosing between some class or some regression, it gives you some numbers. The good thing here is that with a language model, you could ask it to explain its rationale and it to do that. Even though so this is me probably countering the very theme of the conference, so apologies in advance. But I think explainable AI is impressive, it's amazing, but there's one angle to it that we should look at. So if you take humans, right, we assume that human beings are explainable, interpretable, but in reality, are we really explainable and interpretable? So first of all, let's say interpretable implies that you understand the underlying mechanism of why some entity does what it does. Okay. Do we understand fully how the human brain works? No. So then we are not fully interpretable. Explainable implies that each decision this entity does, it could justify it. But I think most of neuroscientists would confirm and tell you that human beings, what we do is post-rationalize our decisions. We don't actually explain why we do stuff. Because we have common sense, we also have social skills. So if you ask why do you do that, I'll give you the best reason that does not make you remove me out of the social circle, right? And so language models also, there's at least some research that shows that they don't always explain things to match their actual reasoning. So there's this whole technique in large language models called chain of thought. And if you, so this is, it's like going through a bunch of reasoning steps to come to some conclusion. The reality is that some studies have shown that if you ask an AI system and it goes through this chain of thought, its reasoning path, and it comes to an answer, when you ask it why does it come to an answer, it doesn't always tell you everything it went through its chain of thought. It's sort of obscure certain information, which makes them the perfect predecessors to at least Homo sapiens, because that's exactly what we do to as well. So explainable, it depends on what the objective is. At least you want an AI system to give you some sort of rationale as to why it made certain decisions, try to defend it. And in at least current use cases of AI systems, you want human beings to supervise the AI system. So if the justification does not make sense to whoever is supervising it, they could reject it. But it doesn't necessarily mean that that is why the AI system chose that decision. It might just be coming up with post-rationalizations that it believes would convince you. So on the medical side, one of the first things we did was we essentially gave our AI system medical exam questions. The MMLU medical aspect to it's a popular benchmark. So we gave the AI system, it actually scored, so there's different ranges. There's professional medicine, anatomy, biology. Oh, sorry about that. Can you still hear me as I'm trying to fix? Okay. So essentially, there's these different domains. We give it to the AI system. The performance usually ranges from 70 all the way to 92 across the different categories within MMLU. So these are some of the questions that you find within the MMLU. What substitutes are available for Crystal, and then, so which is a medication, and then it's able to answer that. Can you describe any potential side effect that users of Crystal might encounter? And then the AI system explains that some of this side effect might involve nausea, taste change, diarrhea, upset stomach, weakness, and the list goes on. Then what does it use as a remedy for? It explains that. Another use case that we've been very impressed by, so some of the use cases, this is also the other thing. It's not always what the AI system itself does. It is sometimes the layer you put on top of it. So in this use case, the AI system was able to write medical report. Yes, that was not, we trained it to do that and it did that. But one thing we did was that we built a software layer on top of it. So what happens is a lot of times when people integrate AI solutions into clinical workflows, they sit outside of the clinical workflow. So ideally, if a radiologist wants to write a medical report and the AI system works something like the way we have here, they would have to see the text and still have to type everything again in some reports. But over here, the AI system actually drafts a report. So it's going to type out a bunch of things, and then the radiologist has the option to edit them. So they can take out, add a bunch of stuff, and then they can download. So that sits much more within the clinical workflow. It's much more integrated. So this is one of the use cases we've been very much fascinated by, and we support several modalities. So X-ray, mammograms, even dermatological images, microscopy, and the list goes on and on. I think we probably support somewhere around maybe 15 different imaging modalities out of this, and then we are still expanding them. So in line with that, even talking about things that we didn't know fully the AI system could do, we've been doing radiology as part of the work we do for quite some time now. So I know, quite a bit about radiology. I'm not a medical doctor, I'm a technologist. So we told the radiologists that, the AI system could do X-ray, mammograms, ultrasound, all of this. Then we visited a facility one day, and we saw there was this interesting looking image. So we asked them what is that, and they said that is an HSG. It's a specialized X-ray. So then they asked us, did you train your AI system? Maybe someday, so they said maybe someday you could train your AI system to be able to support that as well. And we said, well, why don't you just give it a try? So they passed in the image and asked what is wrong with the patient, just the question, what is wrong with the patient? And the AI system was able to pick up exactly what the radiologist had in the report. And they're like, oh, wow. So the fascinating thing about this always goes back to the fact that you don't fully know all that it knows until someone presents some problem, some use case, and then you keep finding out the stuff that it does. But the other exciting thing is that you can be as detailed in the query or as vague as you want. It allows room for that sort of broad range, free-form queries. So if you take, for example, the question that asked to generate compound for breast cancer therapy, that's kind of open-ended, very, very much open-ended. Right now, we are doing an implementation where we are designing antibodies for malaria, and we have very, very specific targets that we are going for. And so the same AI system, this time we gave it very specific targets, and then we've even taken it a step further. So now we've defined a sweet spot across certain metrics. So everything from foldability to melting temperature, we give it a certain range and we're asking it to generate within those ranges. And it's still able to do a number of them. You can also make it to be able to optimize the generation based on the results. So there's this cool, when I prepared this slide, so many things actually has happened since then. I'll share one. We decided that, it's one thing to generate some sequence for some therapeutics, right? Even on the computational side, there's still a bunch of things that should be done. What if we made our AI system an agentic biology researcher? So make it so that it could do a bunch of those processes all by itself. So we tried it and we actually pulled it off. So we created a new version of it where essentially you could just give it a certain target and we'll do everything from generating it, coming up with all the properties, then we'll actually do all the in silico validations, take the result, refine it, and keep this process ongoing, which it was kind of pretty cool to see it working. And now we have like different ideas of how to expand it. But fundamentally, the goal will be to keep expanding this till you have an automated researcher, one that you could just say, cure me cancer, and then it'll be like, give me 6 months, I'll be back. Or maybe you get to a point where it doesn't even need 6 months, it just needs a couple of days, and it goes through thousands of experiments, because the thing is that you can, with computing, you can parallelize things, right? So it doesn't have to be one AI system working. It could spin off thousands of AI systems all working in chain and sharing data across, and you could get the result. So as impressive as some of the things we've done, it's still just the early phase of this. But of course, foundation models are not perfect. They have issues too as well. One thing is, if you run the same query several times, you're bound to get different response a number of times. So how do you deal with that? Those are some of the things. And especially healthcare being a super sensitive field, you don't want to create the impression that these AI systems are 100% perfect. So some of the limitations we've identified, we make it very clear to clinicians. As much as it could do X-rays, mammograms, ultrasound, it's actually quite terrible if you ask it to look at brain MRIs to pick up something like stroke. If you give it, if it's a tumor, it's actually good at picking up tumors, but it's bad at picking up stroke. So communicating those limitations to clinicians also gives them at least the balanced view that look at this as a co-pilot, as an assistant. That does a number of things, but you should always supervise it. And if you disagree, go with your end and not what the AI system says. Because AI systems, sometimes they will do amazing things and they'll make some of the dumbest mistakes you could imagine. And we've seen, so for cancer detection, for example, sometimes there could be just a tiny calcification in a mammogram, the AI system could pick it up. And sometimes there could be this huge, obvious mass that even me as a non-radiologist, non-oncologist, I can see. The AI system would be like, nope, there's nothing there. Which also brings another idea on the theory of foundation models or the theory of AI systems. People use those instances to claim that, see, AI systems are dumb and they should not be trusted. There's actually a current benchmark, I think it's called ACK benchmark, very, very simple task, where even a 5-year-old could solve them. And almost all the powerful AI systems perform poorly on it. I do not think that implies that AI systems are dumb. I'll share my theory. This is just my theory. My theory is that in, let's say, the search space of intelligence, right? There's different configurations of intelligence. We only know of one that is really impressive, which is human. I mean, there are animals and their intelligence at least bears some slight resemblance to ours, right? And so we assume that there has to be only one type of intelligence. We haven't discovered any alien lives yet, but if we did, we might find out that there's different possible configurations of intelligence within the search space of intelligence. What that means is that in a certain specific point of that, in a specific configuration of that, they would have certain strengths and certain weaknesses. So human beings, we have certain strength. There are certain things that our brain is able to do very easily. Then there are certain things that we are terrible at. Optical illusions are limitations of our configurations, and that's just one. There are certain biases. The fact that as humans we think linearly is very difficult for us to process exponential. Even if you study exponential data a whole lot and you see them every day in your daily life, it's still very difficult to imagine that you could start from 1 and then just by increments in a couple of days you would have a really high exponential number. It's very difficult for us to imagine this. And we saw this with COVID too as well. That's one of the issues, because essentially people kept thinking linearly, oh, it's just 10 cases, it's just 50 cases. They couldn't see the exponential growth that was coming. So those are all known limitations of our intelligence. But within the search space of intelligence, it's possible to have other forms, and they might not necessarily have those weaknesses, but our strength, they might also not have. So my argument is that foundation models, I don't think at this point anyone can deny that they do possess intelligence. I'm not claiming that they are living, thinking, conscious entities. That's not the subject matter of this conference. The whole argument is that they are definitely a form of intelligence because they've exhibited that across several use cases, but they would definitely have certain limitations that we humans might not have. And that's totally fine. We still need to leverage them. To connect all that point back is to make the key statement that I am not of the belief that we need to wait for foundation models, large language models to be as humanly, or they should match human performance across tasks before we use them. Because as it stands now, they have superhuman performance on certain tasks, and then they have below human performance on certain tasks. And so we just have to combine it, add it to our arsenal of tools and leverage it. We don't have to wait for this sweet spot where it matches human performance before we use it. Regardless of the use case, if it is medical, we can still use it, but we need to put in safety guardrails, which is super, super important. So once you put in the safety guardrails, then at least you've come to the point where we can tap into the benefits of foundation models, but also keep at bay the dangers that comes with it. So there is, sorry, are we doing a Q&A? So I should probably have asked this before coming on stage. So do I let the full time run, or we can do the Q&A now? I think I'll add the 8 to the 5 and just do more Q&A, probably that. Okay, so that was my ending. Let me redo the ending. That ending was so underwhelming. It was. Let me come up with some statement. So anyway, no, it's the last 2 years has been some of the most exhausting years of my life, because what happened was that we thought we were going to get this system up and running in like 3 months, right? We had this perfect idea in our mind that we're going to curate all this data and just, the transformer architecture is pretty standard, so we're just going to throw the data at it and then we'll get this. It took us building about 4 or 5 versions of this, and towards the end, we were almost facing bankruptcy because we had gone way out of budget for the project, and the cloud service provider was the happiest person in all of this because they made all the money. And they kept calling us, setting up calls, talking about, oh, should we help you to better use our resources? I'm like, how about you reduce the cost? But it's also the most exciting because it felt like we were truly. So there's this famous quote by Ada Lovelace that says, like, in an attempt, it's more like intelligence, artificial intelligence is really about computers, but she was making the point that computers cannot really create something beyond their creator's knowledge, right? That has been a limitation for years. And it's also super exciting that the field of computing kind of started with an attempt to essentially create AI. And because we could not, we settled for basically the computers we have. I think for the first time, we are truly on a path to digitizing intelligence. We are creating AGI. There's a lot of debate to be had whether we are close to it or not, or we've already achieved it. But we are at the cusp of potentially solving the last invention of mankind, which is digitizing intelligence. Because once you do that, everything is almost limitless, right? The limiting factor to doing anything is labor, skilled labor. So, I don't know, Sanger Institute probably has thousands of researchers, right? If you could digitize that instead of thousands, you could have tens of millions or billions of researchers. The effect of that just goes higher. And so we are probably living in the most exciting time in human history, where we are about to make intelligence the most abundant thing on earth. And I'm super excited. I hope you are too. And I hope we can leverage it to solve all the problems that have plagued us for several decades and centuries. Let's cure diseases that, have been with us, HIV, cancer. I truly believe we can solve all of this if we truly scale up some of these AI initiatives and just give it more agentic behaviors. We can solve some of this. Lucky enough, we are now in a period where, even though the Nobel Prize for Chemistry was given to the 3 scientists, to be honest, it was meant for the AI system, which is AlphaFold. It wasn't the 3 scientists that solved protein folding, it was the AI system. I think that is the paradigm shift. We're going to see a bunch of it happening where several fields of science, subfields as well as the main thing, several problems that have been with us for several decades are going to be solved because essentially everything is pattern recognition, and these versions of AI systems are incredibly good at it. So super happy to be here, and then I'm looking forward to all the amazing conversations and the amazing ideas and collaborations that will spin off out of it. Thank you.
Okay, so we have a question online, but I'll start off with my question. So you said feeding these models lots and lots of data. Biological data is very messy. So how much time did you spend curating and adding metadata before you actually got to the feeding the data part?
That's a good question. So to be honest, I said we spent 2 years. Most of it was just working on data, which if we probably had just focused on data from the beginning would have probably taken us less time. So a lot of it was getting the data back, curating it. So not using the whole thing, cleaning it, restructuring it. And sometimes, but the good thing is that, so with this type of AI system, there's what is called unsupervised learning. Oh no, not unsupervised, so self-supervised learning, which is unlike the previous versions, you have to take that data and actually structure it in a certain way. The good thing with this version is that you can actually feed the data in unstructured ways to the AI system. So yeah, we did a bunch of curation, a bunch of quality checks, but also the good thing is that most of the data structures that we had, we could feed it directly to the AI system. Yeah.
And online, someone's asked a 2-part question. Is not this explainable AI approach another form of prediction coming from LLM? How do you manage hallucinations here?
Yes. So the way we manage hallucinations is by actually acknowledging that there is hallucinations and just working around it. It depends. So within biology, hallucinations sometimes could be a feature and not a bug. So for example, if you want, like the version we have for, generating therapeutics, right? Hallucination allows it to take different pathways. So far as you validate them, you can weed the wrong ones out. Because, so what we call hallucination is the model being super creative, right? If you wanted to diagnose cancer, you don't want it to be super creative. Not too much, just a little bit. But if you are asking it to come up with amino acid sequence that would be beneficial for XYZ, you don't want it to just think that there's only one way of doing it. You want it to go out and come up with 1,000 different approaches. And so there's a way to control this. It's also the temperature. So you can, if you go with a lower temperature, it's usually much stricter. If you go with a higher one, it's much wider. That's what we do in biology. In healthcare, again, you just never create the impression that AI systems are 100% accurate. We communicate this to clinicians that always go with your verdict if there's any disagreement between you and the AI system. Let the AI system try to, explain why it thinks it is right. If you're convinced, yes, but if you're not convinced, always go with yours. So those are some of the ways we do hallucination. The other ways, which is connected to the first question, is also about data quality. That makes a lot of difference, right? Like, I would say building AI system is 95% all about data. Because if you have a better algorithm and someone else has a worse off algorithm, but they have a better data, they'll have a better AI system than you do. Data makes all the difference. So to reduce hallucination in one part, the technical side, ensure your data is of high quality, check out for temperature, and then put in safety guardrails depending on the use case you're working on.
We are open for questions.
Thank you for your talk. So I wanted to ask where your data comes from, actually, which is obviously a nice follow-up on what we just discussed, and then also what you do about evaluation, which is a really key issue. Even if you're show something that you know is imperfect, you still have to be evaluating quite thoroughly.
Yeah. So our data sources are actually super scattered. I say this, which shocks people sometimes. We might, I don't know for a fact, because people don't usually also see how much data they have, but we might be the AI lab with the most medical data. We currently have about 7 billion records. So we form a bunch of partnerships across different parts of the world. So across East, West Africa, in North America, South America, in Asia, we curate, so some of this are proprietary data that you wouldn't see on the web, but we definitely also leverage publicly available data sets. So there's biobank data sets, there's biochem, there's a number of those data sets. I can't go into details on all the data we have. This is partially a joke, because it's only a joke. But I can't go into details because then also people start suing you and stuff. And it's partially a joke because there's this whole copyright ongoing battles around data for training AI models and stuff like that. So yeah, we have proprietary data from medical facilities that we work with, from research projects that we've worked on. Then also we have, one key data we actually have is also, which is super useful, is clinical guidelines. So each country tends to have clinical guidelines. WHO has clinical guidelines. You don't want the AI system to just assume that the best treatment for condition A is the same, whether you are in Cambridge or in Accra, Ghana, it's not. So you want the AI system to be aware of the discrepancies involved in all of that. So we feed the clinical guidelines too as well. We did utilize some amount of synthetic data, but I think for the next version, we'll probably use way more synthetic data. The thing about synthetic data is that if you're going to utilize it, just do it with a verifier. So if you're not verifying it, then you might just be passing on the hallucinations of the current version to the next version. But if there's a verifier, you can potentially now generate several times more data than is possible with existing data. With the clinical evaluation, I didn't have a slide for this, but we've actually tested the AI system across about maybe right now, say 50 different benchmarking data sets. So I mentioned the MMLU, I didn't show the result. Okay, I did highlight the results for MMLU. But we've tested it across several use cases, and we have the benchmark results for those. For some of the tasks that do not have existing benchmark, we put together some benchmark and test them for that. So yes, we do validate them, but there's actually a limitation with most of these benchmarks too as well. So in trying to validate AI system, since this is healthcare biology, there's clinical validation, which you go get some medical data sets that has like solid ground truth data from the gold standard, and then you compare it with the AI system, which is what we do. The next step, so currently we formed some partnership with Stanford University and University of Wisconsin, and also University of Ghana and the Ministry of Health in Ghana to do a randomized controlled trial. And this is not even necessarily looking at whether the AI system is accurate or not. That's not the focus per se, because that we've done from just using ground truth data, is to see, does this lead to improved care overall? There are very few research that have actually answered that question, whether AI system leads to improved care. So there's a new research that we are putting together. We'll be doing a randomized control trial to get that data. Sorry, before, oh yeah, let me just say one more thing. I talk a lot, I know. So with the benchmarking, generally this benchmarking involves you taking some question and then some different possible answers, A, B, C, D, and asking the AI system to choose one, right? That usually does not mirror the real world use cases of AI system, because in the hospital, the doctor is not asking the AI system to choose between A and B and C. It's saying this is the patient, da 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 da. So there's something in AI called vibe check. In that case, you actually give the AI system to those who will use it and let them use it and see if it meets their target, and then let them rate it. So that's actually a better way of measuring AI system than the A versus B versus C versus D. Yeah.
Thank you. So we are moving into the next session now. I'm so sorry. But you can ask your questions in the panel discussion. I would like to invite James, who is the Chief Information Officer here in Sanger, and our panel onto the stage. The discussion is on people, data, and systems in AI.
That was brilliant. Well done, you. That was really good.
Thank you.
I don't want to take a seat.
Okay. Where should I sit?
No, just by yourself.
Okay.
Do we have microphones? I'm conscious that we're running a little bit behind. But I think we can afford about half an hour at least, I would think. Okay. Can I introduce myself? My name is James McCafferty. I'm the Chief Information Officer here at the Wellcome Sanger Institute. So as well as doing all the kind of standard IT type stuff, I do have certain responsibilities around data. Scientific data, among other things, and also our informatics. So as you can imagine, I'm very interested in the kind of AI techniques and capabilities that we've heard of today, Francis and Martin. So, as part of this panel discussion, what we're hoping to do is pick up on some of the expertise that we've seen ample evidence of from the different presentations. And I'm hoping, no pressure panel, that we can pull out some learnings, right? So if you're sitting there with problems to do with data or systems or issues around the people agenda, talent and skills, then now is the time to get them on the table, and we'll have an excellent discussion here. For those online, we do have Slido, and I'm hoping someone's got the brilliant. So we'll pick up on questions at the end. So if we allow ourselves maybe about 25 minutes, we can cover off our conversations and then open up to questions generally. So if that's okay, panel, can I ask you very briefly just to reintroduce yourselves, just to remind people who you are, and say a little bit about your perspective, just generally, on what you've heard here and what it means for your own work. So Maria, do you want to go first?
Yeah, sure. So I'm a professor of natural language processing. My name is Maria Liakata. I work at Queen Mary University of London, and also I'm a Turing AI Fellow. And my work has mainly been around different kinds of natural language technology that feeds into LLMs. And I'm particularly interested in sort of the potential that LLMs have for medical applications in particular, and in long contexts, so looking at sort of diagnostic tasks over time, but also in mental health and understanding the reasons behind model decisions. So I think this is kind of in a nutshell.
Great, thanks, Maria. Marianne?
I'm Mariana Boroni. I'm a researcher at the Brazilian National Cancer Institute, leading the Bioinformatics and Computational Biology Lab. And my main interest is in omics data, their integration and application on tumor biology, and with a translational focus to identify biomarkers that could help stratify patients and to have a more precision medicine.
Great, thank you. Alpan.
Hi, yeah, I'm Alpan Raval. I'm Chief AI Scientist at Wadhwani AI. We are a non-profit based in India, and we do work on AI for social impact across healthcare, agriculture, and primary education. Our charter is really social impact, not so much doing fundamental research. We see research more as a side effect of developing models that affect the communities that we serve. So we have about 30 different projects going on across fields. I gave examples of 2 of them in my talk earlier today. What really worries me as we do some of these projects and as we interact with the people that they impact is the growing data divide, sort of the digital divide, I think it's also called, which is sort of a layer on top of the socioeconomic divides that are coming into society. So it's almost like there are these data have-me's and have-me-nots, people who know how to interact with data, contribute data, know what's informed consent, know what is privacy, and those who don't. And I'm worried about the consequences of this on, especially as AI models proliferate, synthetic data proliferates, and so on.
Great, thank you, Alpan. Andre?
My name is Andre Altman. I'm an associate professor at UCL in the Hawks Institute, Center of Medical Image Computing. And my research is centered around trying to understand the genetic and molecular basis of brain disorders often. And that's why I'm looking at brain images and also genetics and trying to get health record data and data out of hospitals and trying to understand really what's going on. Because often we only have very short observations of patients. We don't know their history. We need to guess what their future will be looking like. And it's trying to, getting access to representative data and working with it and create models that are actually bias-free and fair to use.
Great, thank you. And Darlington. Hello again.
Hello again, yeah. I'm Darlington Akogo, founder and CEO of minoHealth AI Labs.
Great, thank you. And thank you, panel, for your time. So, we did share a couple of topics among us ourselves, so hopefully this won't be too much of a surprise. But one of the things that we wanted to focus on initially was about data, and we've talked a lot about it. And I was going to start by exploring the topic, Alpan, if you don't mind, thinking about the kind of learnings that you've had in your projects about how to collect data. Especially thinking about AI-ready data, what kind of learnings and advice would you have to people for doing that in a way that supports AI?
That's a hard one. I think the main learning is it's really hard. But I think specifically there's I'll give, in the context of the work that we do, there's lots of unanticipated issues in data collection. For example, one of the projects that we work on is estimating infant weight from video, and we had to go out in field to collect data from rural areas, from remote areas, from people who typically don't interact with smartphones a lot. And we had a basic version of the model set up, and we had a nice prototype with a nice user interface. And we went out in the field, and as a way to motivate people to contribute data, we showed them how it works. We said, well, here's how you use it. You take a video of the baby, and you get the weight. And isn't that really cool? And they were like, it's not a big deal. Obviously, you're taking a video, you can tell the weight. What they found more concerning was, where does that video of my baby go, right? So there's, privacy is certainly a huge concern. It's not just a concern among the more digitally savvy or literate sections of society. It's also a general concern. So I think respecting privacy is very important, and designing your user interfaces that do that, and making sure that your models are not going to consume PII data. I think that's a real challenge. So one of the things we do as an institute is we don't ingest PII data except when it's absolutely unavoidable. There are maybe 1 or 2 projects where we do ingest PI data, but we tend to, for most things we do, we tend to remove it at source, so that it doesn't even inadvertently make way into our models. But I think that's very important. And then obviously you want representative data, you want data that reflects the way you're going to use the model, and so on.
Yeah, thank you, Alpan. I think it'd be good to come back to the synthetic data issue in this discussion, but I also wanted to explore, maybe Maria, you're best placed to talk to this one, the kind of challenges and the sorts of techniques that you've adopted in dealing with longitudinal data, the kind of time series data. I saw that quite a lot in your presentation. What kind of learnings have you had on that journey?
So I just wanted to add something on the privacy before we go to the longitudinal. So I very much agree on the issues of privacy. And it's not just the PI data, which is obviously the sort of names, and it's also more subtle. So if, for example, you have particular conditions or particular symptoms, or even when you go to longitudinal data, it's even, even patterns of behavior can reveal, private information. So, for example, if we're doing synthetic data generation of someone who's posted on social media, even if you're not looking at what they've posted and sort of paraphrase that, right? So we have a re-identification task to see whether our synthesized data would reveal that person. What is actually challenging is how you sort of preserve the longitudinal aspect, which is kind of this pattern of even just posting at certain times doesn't already reveal something, because you already have a unique sequence there. And so when you move to longitudinal data, it actually, the privacy issue becomes even more of an issue. But then you do need the longitudinal data if you're going to be, let's say, monitoring someone's health. So for diagnostic purposes, whether this is mental health or sort of, looking at how someone's responding or not responding to cancer treatment, and you have intermediate kind of x-rays or scans and things, you do want to be able to compare with what has been before. But the unique combination of the sequences is, though, an extra signature of that individual. And so I think the combination of longitudinal and privacy preserving is a really tricky one.
And what do you see are the opportunities to provide the safeguards? I think Darlington highlighted that quite clearly about having the safeguards in place for that longitudinal private data. What sort of things?
So I think it's about who has access to this, and if you're then working with models. I think in the sort of the longitudinal data that we feed into models probably it's better if it's synthetic, and so we've removed as much as we can of the not just PI but also other aspects. Because I think one of the issues of the language models is how you control what they give back, right? So it might ingesting these informations and then generating it and for a completely different patient, and then revealing information. So we're looking at the moment on how to kind of mitigate this. But yeah, as I said, I think we're looking at it in any case with EHRs, which is some work of a student of mine is doing with NHS England. Okay. But I think yes, the longitudinal aspect still of because it is tricky, and I think that the guardrails there is who has access to this data, and then what actually goes into training models.
Okay, and it's certainly a big challenge. So Darlington, I was really interested in your comments about synthetic data. And you talked about the dangers of synthetic data, but I'd be interested in your learning on when is it right to use synthetic data and when is it not right? Do you have a sense of that you could advise people?
Yeah, I mean, I would say if there's a verifier involved, you could use synthetic data. So a good example is this. I think right now for generic use cases, right, the most powerful AI system would be O1 from OpenAI. It was actually trained, most of what makes it powerful is its reasoning capabilities. All of that is based on synthetic data. So the verifier being that if an AI system is generating some math questions and you have some calculator to verify whether the questions and answers actually match and they're correct, then it makes sense to include that synthetic data. There's a data wall, right? Currently, we are training AI systems on 15 trillion tokens, right? I've forgotten what the wall is, but I think it's estimated somewhere around 200, maximum 400 trillion tokens. But with synthetic data, there's no limit to how much we can go. So verifiers could be things like calculators. It could be simulators that you have in chemistry and biology. Once you have those things in place, we should definitely leverage more of synthetic data. Yeah.
That's a good answer. Thank you. I was going to move the conversation on a little bit. And
can I say the last thing about synthetic longitudinal data? So I think one challenge also is at the moment, the more, the longer your sequence, when you're generating synthetic data, the more possibility is that for errors in the generation of the sequence. And that's something that we need to be mindful of and sort of work towards. And so the sequence needs to be both, I guess, consistent with your, I guess, original sequence, but also within itself. So there's various sort of things to try and assess and evaluate there.
Thank you for that. So I was going to move on to talk about multimodal data, and I think pretty much everyone on this panel mentioned it at some point. And maybe this is a question for you, Andre, because in your work in the Hawks Institute, it seems to me as if you're integrating so many different data sources to try and achieve the medical work or robotics work. What kind of learnings would you have for people who are starting to think about other data sets coming from different labs, different places, different data sources? Any key learnings from you?
Yes, so lots, and there's a long learning process. So one thing that initially was always a problem is, if you think of imaging data, every machine is kind of very unique. They're mass-produced on a certain scale, but if the scanner sits in a Universal Hospital London or King's St. Thomas Hospital or something, it's at least a slightly different signature. And the AI system are very sensitive and pick these things up. So you need to train the models in such a way that actually they extract vendor, device agnostic features. So you have to build that in, which is possible, and you can verify it. And there's then the problem that older data, again, looks different than newer data. So we have newer generations of machines. We want to use the old data. And there's a temporal aspect as well. So we need to try to overcome this, again, with modeling aspects. The important thing is being aware that this is a problem. And then testing when it's impacting results, and if it doesn't, and how, and if it biases results. So, so it's a learning process there. So yeah, be aware where the data comes from, check for biases. And in the neuroimaging field, we started adopting combat, ironically. And we call it neurocombat. But the field actually has, they started off with the vanilla implementation, but then there's specific things to neurodata that they now implemented and improved on the classic combat. So there's a longitudinal version of it and so on. So there's things to harmonize across data sets now. It's one way to move forward here.
Okay, that's good advice. I was going to ask Marianne though, because I was very impressed with your work on ovarian cancer, and particularly the single cell work. And single cell, of course, is quite close to our work here at the Sanger, right? But it seems to me that almost on a regular basis there are new instruments, new insights. Again, how do you and your work go about bringing those data sets together?
Yeah, sure. Well, Going back to this multi-omic problem, when we are integrating different omics, I think we have this problem of having a great data set because right now there are only few cohorts available where they have profiled different omics of the same patients, and sometimes, they are not accessible to everybody, so it's something very limited. And when you are integrating data from different places where they have profiled different omics, then you have this missing data problem, which is also very difficult to deal with. And also, when you are scaling to technologies such as single-cell data or even spatial transcriptomics data, then the number of features scale up a lot, and then you need more powerful computers, and this again hits another problem, which is access to this kind of instruments. So working with this kind of data in low resources countries, it's very challenging, and I think we are very creative in a sense that we are trying to analyze this data and come up with new solutions in terms of reducing features to be more like to reduce the cost of like the computational power and so on. I think that's it.
So, well, thank you for that. Can we just touch back on security and privacy? We did talk a little bit about it earlier. And one of the things that Tim Howard in his presentation yesterday struck me was this idea that AI models can embody the data that they were built with, and there's issues of security and privacy around even publishing models. And I wanted to get a sense from the entire panel as to the extent to which that's an issue, and how can we manage around that. And maybe Maria, you'd like to touch on that first.
Yes. So I think, one solution is to try and, as we've said, sort of train on synthetic data when it comes to really sensitive, records and so on. And I think, though, that making the weights of models available, so in kind of open source models, is important. And so there is obviously this juxtaposition between the possibility of, if you sort of try and if you have an open source model, is it sort of more open to attacks? I think that in the end, I guess if you really have issue with sensitivity, we need to have a lot of evaluation for this. It's a big open question, right? How do we properly evaluate for these models? How do we, properly check for privacy leaks, and then put in the mitigation strategies? But I wouldn't sort of not share open source models for that reason. But yes, if it was strictly proprietary data that we couldn't be sure that it wouldn't be accessible from attacks to the model, then I guess I wouldn't share models trained on those particular data.
And Darlington, I'd be interested in your perspective on that. So it seems to me as if Maremi is dealing with quite a lot of patient data being trained. How to protect that if a model does come under attack or investigation?
Yeah, there's a number of things you could do. I think we've highlighted them. So yes, essentially, okay, so I do have a question. I was trying to not bring it up, but if, for medical use cases, yes, I can see that being a problem. You give a use case for social media, right, where due to the style of post, you could potentially identify who it is, even if you remove the PIIs. But in that use case, the challenge I have with that use case is that like social media is actually public data, right? Anyone could go on your Twitter page, unless your account is private, which if it were private, probably whatever crawler is being used or whatever scraper is being used wouldn't get access to it, right? But if it's public, anyone could go on your Twitter and see your tweets either way. For medical, yes, but the most important thing for us is to remove that PIIs, right? So even if, let's say, someone were to some way, somehow get access to the data, they could see, okay, there's a patient that has breast cancer and they are on these medications, but they don't know the name of the patient. But PII is not just names, right? So if you don't know someone's name, but you know someone's date of birth, you know their gender, and you know what city they are in, you could always, just align that with any publicly available data, and then you probably know who it is. But so PII includes those two as well. And the balance between that is always tricky, right? So if you are overly protective, you end up not doing anything with AI systems. You don't even give them any data because you're too worried. But if you're also too much swung on the other side of the pendulum, then what happens is that you jeopardize people's privacy. So we always try to strike that balance. But some of the safety guardrails is actually making the AI system pretend to not be capable of things that it's actually capable of. I'll give one good use case. So we found out that our AI system can actually generate upon command highly toxic compounds targeting specific things. Mm-hmm. If you told it that generate some sort of compound that targets the nerves and you describe it, it's able to generate it. If you want it with higher toxicity, low toxicity, it's able to do that. Clearly, we don't want the general public to have access to that. So as part of the safety guardrails, if you ask it those questions, it will tell you, I cannot do it, which is not true. It can do it. So there are a number of those use cases that we've identified that it could do, and we just tell it to refuse to do it. But yeah, the question I passed on to you. Yeah,
I like that example though, Darlington, and it just shows the power of the technology, and it has to be used appropriately. And for personal identification, I don't know how true this is, but I remember being told that just 6 simple, non-personal questions will identify pretty much anyone in the UK. It doesn't take that much to do it. Can I ask the rest of the panel any other kind of views on this idea of the model sort of embodying the reality that was used to create it, and how we protect that? Any other views?
I mean, in medical imaging, we have the same issue. And so there was a paper, I think, that linked brain MRIs, which contain part of your skull, to actual images of people. So that's, of course, concerning. In the end, it wasn't that great a use case because it was a limited set of which pictures the system could pick on, so 1 out of 20 or so. But still, as a consequence now, for many stuff, when we share data, it's actually problematic. We cannot just share the clean MRI data. We actually need to deface it. So we essentially delete part of this, which again might change how the data looks or is being interpreted, because it's not something that would be used by the clinician, like a defaced image. They wouldn't put that into any system. So then an alternative is to create generatively create a standard face on top of it. Again, it changes kind of the data we're working with, but this is something we need to think of in terms of identifying and de-identifying data, so it makes things a bit more complicated. But it's one case.
Okay, if there's no other views on that, I was going to move on, and this is more about the kind of people side, particularly thinking about the fact that so much of our work is an intersection of different domains, between biology and the plethora of domains in there, and computer science and data management and data engineering, those kind of things. And I'm conscious there'll be a lot of people here either recruiting or trying to develop people in their teams with those kind of skills. And again, I'd like to ask everyone on the panel, their learnings and their suggestions for how to attract the right talent, how to develop those kind of skills, and also a little bit of how to deal with the intersections. I always say, is it easier for a biologist to learn about AI, or does it go the other way? So just a bit of insight onto that would be helpful. And I don't think Alpan has spoken for a while, so do you want to go first on that one?
Yeah, I think that's an interesting question. What skills do you look for, and what skills do you develop? I think it's certainly easier for people from more quantitative areas to pick up domain-specific knowledge. For example, if they're working in biology, I know it's probably easier for this may be a controversial statement, but easier for people from a quantitative field like computer science or physics or math to pick up biology than the other way around. But I don't think you can replace domain knowledge. So there has to be a willingness and an interest in the domain. I don't think you can just be an AI expert and sort of generally work on problems, unless you want to do fundamental research in AI.
Yeah.
But you have to understand the domain. And one of the problems that I've seen over the years is with the advent of deep learning, there are a lot of young people just throw a neural network at a problem without thinking about it. Right? I don't know if it's a problem in the UK, but certainly we see this in India. You give them a linear regression problem and they throw a neural network at it. And so this is a danger, and I don't think they understand. They don't try to model. They don't try to understand the data, understand what are the inputs, what are the outputs, what features might be useful, what features are probably not useful. So everything we learned in the old days when we were doing feature engineering, I think is still important, just in order to understand the problem. And I think that goes a long way. So I think some of these skills, data skills, curiosity about data, willingness to understand the domain, in addition to the computer science skills. But I don't think it's optional. I mean, I think you really need these other skills.
Okay. Thank you, Alpan. Marianne, do you have a view? I'm conscious people talk about T-shaped skills and V-shaped skills and things like that. So for your research group, I guess that must be something in the front of your mind.
Yeah, for us, mainly most of my students, they are transiting from biology to the computational field, so it's the opposite, the majority here. And I agree with you, for us it's more challenging because, for them to learn all those computational stuff takes a while. But I agree with you that this is a very collaborative environment field, and there is no way of, you avoiding this intersection between experts in biology and experts in machine learning and data science. And regarding your question about attracting those people, AI per se, it's a word that make them very curious about. So to attract people to this area, I think it's super easy. The problem is to keep them in this area, especially in academia, because at least in Brazil, and I think I can talk regarding South America, the salaries in academia are not competitive regarding salaries in industry, right? And the way I see we filling this gap with header increasing salaries, then sometimes this is not possible, but I would rather invest in training, so then we can spread and enhance the capacity in those locales.
And it takes a kind of individual attitude to want to pursue a career in research as opposed to moving into the finance sector, which is where a lot of people go.
Exactly.
Maria, do you have a perspective on it? Because I'm conscious you had quite a lot of collaborators listed in your work.
Yes, so I'm quite used to now working across disciplines. And I think there's great value in having multidisciplinary teams, and also both in terms of the experts involved, but also having students with different perspectives, coming from different backgrounds. Because obviously, as everyone said before, obviously the people who have a numerical background, whether this is in maths or computer science, are going to pick up the computational algorithms more quickly. But I think the perspective on the problems is really important. And sort of intelligence does not just manifest in sort of being able to write algorithms and understand algorithms. And there's some really bright people I've worked with who do not have a computational background, but are very good at thinking about the problems. And so I think you need people with kind of both the sort of understanding of the problems and being very good at sort of the problem solving. And I think that's where real success comes, at sort of bringing these two together. I mean, you have individuals who have both, right? And that's quite rare and amazing when you find them. But I think for teams, you do want to have multiple perspectives, and you just don't want people who treat the different problems as all being the same. Yes, there is an element of there being pattern recognition everywhere, but it's sort of understanding the data and the domain problem is really key.
Yeah, absolutely, I would agree with that. And I was going to ask Andrea kind of follow-up related to the skills side of things, because it seems to me more than anyone on the panel, Andrea, you're having to deal with so many different moving parts around the different skills, the capabilities that you're looking for, the deliveries and the like. It must be very hard to bring people on in that space where you're dealing with so many different modalities, plus the robotics, plus the people side, plus the medical and clinical side. So how, in your experience, what's the best way to bring people on in that kind of environment?
Curiosity.
Good one.
I mean, it's different people. So we have some people who are more on the engineering side, and then people who are interested in interacting with clinicians. So in the center, usually we have clinical, also in the institute now, clinical co-leads, to bring that expertise in and make themselves readily available, because it is exactly that domain knowledge that makes or breaks something that is useful. Because we often see, and that's especially in the Alzheimer's field, the data is available, and then research groups go there and say, oh, I'm taking brain scans and I'm making a classifier for Alzheimer's against controls. But nobody in the clinic needs that. And that's paper coming out, is this performance, but this is, it's a toy problem. And you have to cross-talk permanently, and people are interested in trying to solve something like this in order to make something that's actually relevant. And you don't waste anybody's time and compute resources, and try to engage with people, with stakeholders very early to see what is actually the problem they want to have solved. So then it turns out like it's not Alzheimer's or not, it's like, oh, somebody has a memory problem, will they develop Alzheimer's, yes or no? That's really the clinical challenge there. And yeah, I mean, you need people who are curious, and some people, that's why we're also cohabitating with the AI Institute, for instance. So these are people who are doing mainly foundational AI work, and they just do a lot of formulas and develop new stuff. And then in the end we see, oh yeah, that could be useful to us, and then we try to mix and mingle. So it's having different people, and interdisciplinary team means you have different people with different skill sets, bringing together and trying to be willing to engage with each other, and try to translate between each other's language as well.
What comes down to people. And Darlington, I was going to ask you your perspective on it, not just from the point of view of developing skills, but I think you particularly mentioned the complementarity across different disciplines. How do you manage that? What kind of advice would you give to people?
I mean, my fellow panelists give very brilliant answers. I don't know if there's any more I could add to it. No, I would say, so on one hand, sometimes it's just best to put people of different backgrounds in the same space and just let them have like very, very long conversations. Yeah. I've seen that to be very useful. I mean, you could have like some specific topics that you want them to discuss and come to some conclusion on, but if you just let them have like those long conversations, so many things develop out of that. But for skill sets, what I've realized is this. So this is what we do. So first thing first is set highly ambitious goals, because it tends to attract like super smart young people. And then the next step is that we don't look for people who have, like, especially on the computational side, we don't look for people who already have the skill set of LLMs and foundation models. We're just looking for super smart young people. From my experience, we've been able to train people in a period of like less than a month, especially if they already have some computational skills. So if they already know computer programming or they've already done some machine learning, they can go from that to knowing how to train foundation models in like a month. And I am of the belief that people who actually come from biology will find it easier to learn AI. Because to be honest, like, the AI stuff's not rocket science, not really that complicated.
Don't tell everyone, don't tell everyone.
Like the transformer is a very simple architecture. So it's easier for them to move on that end than the other way. That's from my experience what I've seen. So if you have smart people and you give them a really tough problem, they'll go figure it out. Like, they might overestimate, which is what happened. We thought we could get it done in a couple of, like 3 months, it ended up being 2 years. That will happen, but they would eventually figure it out. So, and I think a bunch of labs are also doing the same thing. So OpenAI, Anthropic, they have this fellowship program where they are looking for people who have background in like biology, physics, math, and then you take a couple of months to transition into AI. And those people are some of the smartest people you meet, because they are not just coming with an understanding of neural networks. They're coming with ideas that have not really been exploited yet within neural networks. So yeah, I see that actually works much more. But have this multi-disciplinary team and just let them hang out. We have like games where, like right now we are super obsessed with our 4Connect. So play 4Connect and just hang out, have conversations, and so many interesting things come out of that.
Good advice, thank you. And thank you to all the panel. I think we do have time for 1 or 2 questions, either in the room or on Slido. And again, I would stress, we've got a lot of expertise and experience on this panel, so do make good use of it.
So we have multiple questions online, but if it's okay, I'll start with my own question. There is huge diversity, like James said, from biology to physics to computer science, but also you guys are representing 4 regions in the world, and industry, charity, as well as academia. I would like to hear what would be the golden data infrastructure you would like to see across your regions, where you could safely share data, have privacy, have the ethics taken care of, and do this amazing research that you all want to do. What does that look like? And with all the regulations and the bureaucracy we have, how do we get there?
Okay, so Priyanka never asks an easy question, right? Okay, so that's a toughie. In an ideal world, what kind of infrastructure, platforms and setup would you like? So who wants to pick up that one?
I can start.
Oh, is that because you've got it already, Maria?
Because I've been thinking about it, yes, because data is such a plague for us, right? You don't want, you have always the issue of having getting access to the data, and sort of different researchers. If some researcher changes in your team, can they still access your data? What happens after the project is over? There's so many issues around sort of data preservation, data access. And I think that it's not something that individual research groups can do or should be doing. So there should be more sort of centralized places that sort of curate the data, look after the data, and perhaps these could be made accessible through safe data environments, so SDs, which have already started being set up. Now, having worked previously with data safe haven environments, they can be quite quite hellish to work with, really. Especially, we tried to set up a shared task in a data safe haven environment. In the end, it didn't work because we couldn't be updating the needs for the models quickly enough for that to happen. So we need to sort of make these environments flexible so that actually people can develop their code and solutions at sort of a realistic time, and because obviously when we're developing our models, we don't necessarily know everything we will need from the start. So allow this kind of iteration between sort of access to data, model development in a way that's sort of safe for the data, but also flexible for the researchers. And I think that should be, projects, individual researchers and projects shouldn't be struggling every time to get data access and in sort of data, different kinds of versions of the data and so on. So I think that's my view, and that's also how you could protect data as well. So that you don't in the end, if you were, for example, to have benchmarks being set up that evaluate some of these models, they wouldn't get ingested in the new iterations and the new versions of the models. So if they were sort of in a sort of secure kind of environment where you're posting the model, but in making sure that it's not sort of leaking data back. So I think that would be my kind of ideal. Yeah.
No small ask. Any other views from the panel? What would you like in an ideal world?
I don't have sort of a holistic answer to this question. I've never thought about this. But I think in an ideal world, I'd want the data annotation problem to be solved in a way that's not exploitative, but still human. I don't think synthetic data is the answer. In fact, there's been recent work in the context of LLMs that shows that when you go through the synthetic data cycle, LLMs generating data, and other LLMs trained on the data that's generated, you get model collapse eventually. And I'm worried, in the biological context, we already have all these structures generated by AlphaFold out there. There's going to be more synthetic data out there, and without watermarking, without ways to identify or distinguish between synthetic and non-synthetic data, it's going to be very hard to train models. And you will need human-generated, you will need human annotations. Currently, large-scale human problem, but I think that problem needs to be solved.
And it's certainly a problem. Maria and I were talking a little bit about this, with more and more AI-generated information pouring onto the web, pouring onto social media. It's almost as if now is the last opportunity to fill your boots with real human-generated information, right? Because from now on, there won't be so much of it, relatively speaking. Any other views? Any other items for an ideal world? Okay, well, do we have other questions?
Yeah, we have lots of questions on that. So Adam is asking, delivering ML projects requires diverse expertise. In your experience, which skill sets are undervalued or under-recruited when building ML teams?
Undervalued and under-recruited. Okay, that's an interesting question. Any takers on that? Thinking, I guess, in the round about building up a capability, what are the undervalued skill sets? So I think Darlington highlighted this idea of people working together, and I think Andre was talking about a kind of problem-solving approach. Any other sort of undervalued skills?
The willingness to do the dirty work, to data clean. I mean, everybody usually, especially in university, comes in and wants to train their neural network, for better or worse. They're not willing to prepare the data. So that's definitely, if you want a good model, and you said it, you need good data. So the willingness to dive in, engage with it, and see, and try to understand first, what is good, what is bad, what's causing problems. I think that mindset is undervalued at the moment. So it's not, and that's not a pure math skill. That's really just down to, getting your hands dirty.
I think also research engineers. So these are not just software engineers, but they're people who can understand the problem. So it's usually people who have PhDs who've worked in research but are also very good developers. So I think that's quite a rare skill set, and sort of they can pick up prototypes and sort of create hacking at the moment. Because it's sort of the, making the transition between, having a paper and some code to actually making some impact.
Yeah, that's a good point. Now, do we have time for one more question?
I'll ask the most voted one. So when benchmarking models, how can one reconcile transparency of that research while avoiding incorporation of the benchmark into the next model's training?
Okay, well, benchmarking is fraught with problems, we know that. Maria, I'm looking at you already.
Yeah, so I kind of hinted at this, that I believe that we need to protect the benchmarks, and so a way of doing this is some kind of secure environment, I think, where essentially the model has to be evaluated there, and sort of it's not widely shared. Now, the exact details of that implementation we're still trying to work out, but I think that's kind of the model that I would think would work. And again, I don't think this should be individual research groups, but I think that's something that a more central organization should be essentially. I don't know whether this is going to be something like the AI Safety Institute or Turing or who, but I think in the end, sort of evaluation that is being developed by individual groups should be coming together, and sort of models sort of passing through maybe some kind of certification in sort of this kind of more central body.
Great. Well, shall we wrap it up there? I'm just kind of conscious of the time. Thanks very much, everyone in the room, and also on Slido as well, some great questions. But special thanks to our panellists for bringing a bit of humour, a bit of expertise and a bit of insight into these tough issues. So special thanks to Darlington, Alpan, Maria, Andre. Special thanks to Mariana, who has now done 2 of these. So thank you for that. And let's give them a big round of applause. Thank you very much. Thank you, panel. Now, I think we stay with me, do we? Yeah. I have the honour of giving some closing remarks. We are overrunning a little bit, so I've decided not to give you the 1-hour speech you'll be glad to hear. And it's normal at the close of an event for someone just to give a little bit of personal reflections on the event. So I will do that, but I also wanted to just give you a little bit of an insight into the work that we're doing at the Sanger. So for those of you who aren't familiar with the Sanger Institute, our origins come from the Human Genome Project, which goes back 20, 30 years. And we contributed massively to that. I think about a quarter of the entire initial human genome came out of our labs. And since then, we've been picking up on all manner of genomics-related research. So we're now quite a sizable institute. We have about 1,300 staff, and about half of those are research scientists. We pride ourselves on science at scale, and that basically translates into generating massive amounts of data. So as the CIO, I get to see the sharp end of that. We've got about 90 petabytes of the stuff. And that's by no means the full story. We pass a lot of data into EBI, who provide that publishing capability, and they have about 4 times as much data. So yeah, we're very much about open science, sharing that data. And it did occur to me, just listening to some of the presentations, it's largely a huge resource for the kind of projects that we've seen in this room. And I know that both John and Priyank will be very open to discussions around collaboration as we go forward with it. The main use cases for AI and ML that we're seeing in our work, at least, there's quite a chunk around modelling cellular mechanisms. There's a lot of work that we're doing in histology, image analysis, spatial type techniques. We do quite a bit of mutation prediction centred around genomics, and it was great to see a few of the poster papers just yesterday covering that kind of thing. But we also use AI in other kind of scientific related ways. So one of the new ones that's quite exciting is around gene editing. In fact, just to give you an insight into the growing confidence in the genomics community, we often now don't refer to gene editing, we talk about gene writing, right? And if you get the subtleties in that, it gives you an indication on the perspective. We've been working on generative models, particularly to feed into synthetic biology, which is a big thing for the future, and also de novo sequencing. So one of our programs is the Tree of Life program, and it aims to sequence the entire genomes for all species in the UK, so that's over 70,000 different species. And that's de novo sequencing, and if you think that it took, 10 years, more than 10 years to come up with the first human reference genome, the Tree of Life program are churning them out on a weekly basis. It's a massive endeavour. So I wanted to give you a sense of the kind of AI aspects of what we're doing, so automating those kind of processes as well as doing the science. So, as regards general reflections on this event, I don't know about anyone else, I have had a fantastic time, I really have. Just listening to the presentations, I've been so impressed with the kind of practical nature of what we've been talking about here, the workshops that we've had, the hackathons, the tutorials, as we all get up to speed in some of these new technologies. And I think that's really important to have that for what is a very exciting and emerging field. And I wanted to just highlight a few things. One of them is, and we kind of touched on this in the panel, a lot of what we do is about getting the right outcomes. I know the tech is great, you know, the data is wonderful if you work through it, although I take Alpan's point about the curation piece. But all of that together is just for one thing, and that's the outcomes. And we are in a privileged position when you think on it, and I think Darlington touched on this. We're in a privileged position for right here, right now, the tools that are emerging, the technology, the data, to make that work for society. And it's as much as possible a global aspect to this. I think COVID certainly made that very clear to all of us, that we do not live on an island. Allied to that, we often hear talk about the digital transformation of science, because so much of new instrumentation, new techniques, new approaches, across all aspects of human endeavour, it's digital, it's data, it's forever growing. Well, the same applies to science, and we'll see more and more techniques like AI and automation play through into science, so that it doesn't just make science better, faster, cheaper. It will change the way that we do science. And I think we've seen, as we've talked about the foundational models and the like, that the changing way that we do science will make, well, we call it dry lab, you know, working in informatics, much more important than it has been previously, where we'll see scientists, first of all, going to foundation models to evaluate potential hypotheses, try out the scientific questions. So that will, again, change the nature of what we do. And I think we saw here over the past few days quite a clear indication of that. I wanted to touch on the nature of collaboration. Science is a team sport, and certainly AI in science has got to be a team sport. I reflect back, so this shows my own, I did a PhD in computer vision, and that at the time it centred around competition. So the ImageNet competition, and more recently the CASP competition, where different teams were working on different AI approaches to solve problems. Yeah, I get that, that's fine. But generally it's about the community, and the community will move forward or not. And it's been so lovely to see so many researchers and so much insight coming from right across the planet for all of this. It's been so wonderful. But again, I wanted to stress that. I also wanted to stress that it's not without its challenges. I think we've talked about explainability and trustworthiness. We've talked about hallucination and the like. I would also add into the mix scalability, right? And this idea of being able to develop new techniques that are sustainable, that don't burn up the entire planet's energy resources. And that's a challenge not just for this community, but for AI generally. And I think we as a bioscience community can be working with AI researchers to help them take on some of these challenges. A good example of that, thinking again about foundation models, is this idea of pre-trained models. We need to be doing more of that, but also making sure that the models that we use are effectively interoperable. And I was talking to Matthew earlier about some of this. So there's some good work happening in that space, that you can almost have a kind of pick and mix approach on foundational models when trying to model biological artifacts. And the ethics side of things, and I don't mean ethics in a kind of soft, fuzzy way, but it's down to aspects of governance for what we use these models for and what we train them for. So for example, in the Sanger, we've just recently adopted a policy about increasing the diversity of our research data and our research generally. Those of you who are familiar with genetics, there's been a massive, just generally a continued focus on people of European origin. But when you think on it, that's tiny compared to the genomic variation across the planet. So we've got the message, and I think it applies very much here about making sure that we do avoid bias, and we do work with diverse data sets. The last point I wanted to make was some of us went out to dinner last night. We had a fantastic time. I don't know what it was like on some of the other tables, but we were talking about what is science going to look like 30 years from now. No small challenge. We had some great ideas on our table. The best one, where's Marianne? The best one was, we'll all end up with little devices that fit in our ear, right? And someone's talking to you maybe in a language you don't understand, like Portuguese, does the translation. And then how does that fit with augmented intelligence, where you're going to start end up with chips inside your head and stuff like this? So that may all sound a bit futuristic, but when you think 30 years from now, and again, we saw it in some of the presentations, the idea that AI models can start to form hypotheses and start to perform their own investigations in the world, and I think Darlington brought this out really well, it accelerates the science hugely. One of the techniques that we are looking to do further work on is this idea of lab in the loop, where the AI model can effectively request experiments to be carried out that feeds data into the AI model. So the AI model is on a journey of discovery. Although I do like Darlington's idea that we'll end up with about 10,000 scientists in the Sanger. I look forward to that one. Okay, so it remains for me to thank everyone for attending this event. Not just the conference, but the workshops, the tutorials, and the posters and the hackathon. I think it's been a fantastic event, so thank you very much for that. These things do not happen by accident, so special thanks to John and Priyanka and all the team who have pulled this together. Special thanks to our speakers as well. The presentations have been truly fantastic, and I personally have learned a lot from them. Looking to the future, building on the success of this event, I'll be very keen that we keep this going. So please do keep in touch with Priyanka and John. As I said, there's lots of opportunities for collaborating in this space, particularly for institutes like the Sanger that are data rich. So please do keep in touch, and we'll keep in touch with you as regards future events as we take this forward. So what I would suggest is that we give a round of applause to our speakers and to our organisers. Well done. Now, I hope that wasn't too painful, because I was standing in between you and lunch, not literally, because it's outside that way. So I think there's a kind of packed lunch that you can take and go. And I think there might also be, for those who haven't yet had a tour of the campus, there might be an opportunity to do that as well. So if you talk to John and Priyanka sitting down the front. So thanks for coming. Please do have a safe journey home and reflect on what I think has been a fantastic event. Thank you very much.